to the cloud, man of science. Okay. Okay, that's enough for today. Anyway, I'm here again. Well, this is redundant, isn't it? What we're going to be doing is, ignoring my tattoo. What we're going to be doing is we are going to be talking about a physics problem I gave you in class today. You being AP1 students. Anyone on the internet, I didn't see you today. I'm not a weird stalker or anything. Anyway, so let's look at the stuff on Colby's locked phone. Because, you know, the problem's on there. There we go. Yep, nothing weird to see there. Anyway, so lupita. I like the name lupita. It's like little Lupe, right? Lupita is on a run. She starts running at a constant speed of 5 kilometers per hour. So, she's running at 5 kilometers per hour. Cool. Okay, and then after 10 minutes, she decides to start running up a hill. Also cool. So let's make this a little lower. I'm going to put that down here. 5 km, 4 per hour, for 10 minutes. Once again, red flag went up in my mind here because, wow, my handwriting is really bad when I write low. It just got worse. Anyway, then she ran up a hill, started running up a hill, and she went 10 kilometers per hour because she's like, let's get this hill over with. Hills kind of suck, right? But unfortunately, as she's going up the hill, she slows down. She gets she slows down, 2 kilometers per hour every minute. So she slows down 2 kilometers per hour every minute. So if you know, that's an acceleration, right? So we have a speed, and acceleration. Okay, so how do we do this? Okay, well, the first thing it says, how long was the hill? Okay, let's figure that out. Well, first of all, there's some problems with everything up here right now. Oh, by the way, it took her 3 minutes to climb the hill, by the way. Just so we know that. It took her 3 minutes. Okay, well, the problem is we have minutes, we have hours, kilometers, hours, kilometer hours, minutes. We have minutes everywhere. We don't want minutes everywhere. We want hours. So, what I'm going to do is I'm going to convert this in hours first. First step, right? Sorry for the bad handwriting here. Oh, that's okay. It's all right here. It's all here. I made up this question. Okay, so, well, to figure out the minutes into hours, we're just going to take 3 divided by 60, and that's going to convert it into, well, it's going to be 0.05 hours. So let's get rid of that. And then write H for hill. TH equals 0.05 hours. Cool. Well, and here we are at 2 kilometers per hour per minute. Well, I said per hour. Well, if we're going 2 kilometers per hour, we're subtracting 2 kilometers per hour per minute. Imagine if we went for an hour, that number's going to be a heck of a lot bigger, right? So that should be ahead of what we're going to do here. We need to multiply that number by 60 to get it to the right thing. So 2 times 60, that's 120, right? So that's actually negative 120 kilometers per hour now. Cool, we fixed it. This one down here, got to do the same thing, right? Well, 10 divided by 60 gives us 0.1666666666666666666666666666666666667. We'll say 1.7. Okay, hours. 1.7 hours. Cool, look at that. Anyway, what were we trying to do in the first place? Well, we're trying to figure out how long the hill is, right? Okay, so first, we know that we are starting at 10 kilometers per hour. So we start at that speed, 10. And then we know that we are subtracting 120 kilometers per hour over the period of 0.05 hours. Okay, 0.05 hours. Cool. Now you're probably asking yourself, like, why did you put the speed next to the time? Well, I want to get a distance, right? And by the way, this is not speed. This is negative 120 kilometers per hour per hour. So this is an acceleration. Okay. I'm probably setting this up wrong, but we'll fix it here in a second. So let's think. All right. We're going forward, and we're slowing down by this much. Okay, what's my formula for this scenario? Well, distance, let's think of our kinematic equations. Distance, y, is equal to some starting velocity times time, plus, but this case it's going to be minus because we're going negative, so we'll keep it as minus 1/2 at squared. Well, that's easy enough. And this will give us our distance. Okay, we have to use this equation because we have an acceleration. If we did not have an acceleration, ignore this one above. I was trying to jump ahead, and I don't want to confuse anybody, even though I probably already have. Keep in mind, we are using this fundamental equation to solve this. Okay, and those of you at school today, we're talking about graphing a lot, and like, what's an acceleration graph? Okay, we're going to do that in the last step. We're going to say, okay, now what does the graphing for stuff look like? Right now, we just need to figure out what the heck she did, how far she went. Okay, cool. So starting velocity. What's her starting velocity? 10. We got that one down. That's easy. 10. Well, how long did she do it before? Well, she did it for 0.05 hours. Remember that was that 3-minute period up the hill? We have to include that there. So 0.05. And then we subtract that from 1/2 a. Well, a is not 9.81 in this situation. It's not gravity. She's slowing down because she's getting tired. And that amount is actually this 120. 120. Well, I'm just going to simplify this right now. What's 1/2 of 120? Let's just simplify that so we don't have to write all that stuff in there. That's 60, right? Minus 60 t squared. Okay, this has got a heck of a lot easier, didn't it? Well, let's do it. Well, 10 times 0.05. 10 times 0.05 equals 0.5. Pretty simple. So, we'll write that here. 0.5. And you know what I'm going to do? Just while we finish this problem, I'm going to get rid of all this stuff down here. We're going to put it back up in a second. Okay, but 0.5, and we're going to subtract whatever this is. And now you're probably looking at this saying, oh, we might get a negative number. We're not going to. T is such a weird number. Oh, what was T? I just erased it. That was that 3 divided by 60, right? T is 0.05. Cool. 0.05. Well, let's do this. Let's do 60 times, yeah, that was a close one. I almost didn't remember that. 60 times 0.05 squared becomes 0.15. 5. Well, look at this, guys. This is how simple it is. Well, what's 5 minus 0.15 minus 0.15? We get, 0.5, sorry. 0.5 minus 0.15 gives us 0.35. And you're asking, okay, 0.35 what? Well, we did it with kilometers per hour per hour. It's 0.35 kilometers up that hill. Not bad. Okay, the next question, you can't see it on the phone because it locked, but that's fine. The next question was, what was the total distance? Well, that's easy enough. She started at 5 kilometers per hour at the beginning of the hill, and she did that for, I believe, 10 minutes. Oh, actually, unlock that. I need to print these out. Make it a little easier. Oh, yeah, so for 10 minutes. That's right. 10 minutes. And then we decided that 10 minutes was actually 0.1. 10 divided by 60 was 0.17 about, right? That was when I said 1.666666667. But 0.17. Okay, 0.17 hours. Cool. So you have a speed, you have a time. Distance divided by time equals speed. Okay, so we rearrange that. Distance divided by time equals speed. Let's rearrange that and solve for distance. So it's just speed times time, right? Look at that. Distance equals speed times time. Okay, sorry my whiteboard's so small. We're going to get a bigger one eventually. Okay, so speed times time, 5 times 0.17. So we'll multiply this by 5. We'll get a distance of 0.83 kilometers. And of course, we're going to add that to that. 0.83 plus 0.35 gives us a distance of 1.183 total kilometers. Look at that. Okay, the first part of that question, really hard. Second part of that question, really easy, just basic speed equation. Basically all we did here is we practiced using our one with no acceleration and using it with our one with acceleration. Okay, the last part of that question. What was the average acceleration of the trip? Okay, this is sort of a trick question. I'm going to draw the picture of the trip again really quick, and you'll see why. Okay, here is the question, or the scenario again. She goes forward, 10, sorry, I keep doing that, 5 kilometers per hour for 10 minutes. Cool. Well, what's this? This is a speed, and this is a time. Keep that in mind. Okay, then we have a speed that we start at, but we really don't have any time for it, right? It's like 10 kilometers per hour, and it's like that instantaneous beginning, right? And then during this period, we have a negative 2 kilometers per hour per minute. And remember, we simplified that, and we ended up getting something like, what was it, negative 120 kilometers per hour. Cool. And we know that went on for 3 minutes, or which is the equivalent of 0.05 hours. Cool. Well, just like average velocity, for average acceleration, we have to take all our velocities, right? All our velocities and divide by all of our time. Okay, so what is our velocities? We have 5 kilometers per hour. Well, that one happened. 5 km per h. We have 10 kilometers per hour. And then we have a acceleration of negative 2. Oh, by the way, this is for point. You know what? I don't like this. Let's not do that part of the problem, because what we're going to end up having to do is break this apart, the acceleration, and I don't want to do that yet. We're going to do that later. Okay, let's just get to the big important thing. Let's look at the graph, so what she did. Okay, this starts pretty easy. Okay, if we look at our distance time graph for Lupita, distance time, what did she do at the beginning? Well, she started out 5 miles per hour for 5 kilometers per hour for 10 minutes. So for 10 minutes, we should have like this straight diagonal line, right? Because she stayed at the same speed. Okay, this is the sign that we have a constant speed, right? And then she jumped up to 10 kilometers per hour. So this is 5, and this is 10. So she only jumped up to 10 because she's like going to start running really fast up that hill. But then unfortunately, as she starts doing that, she starts immediately slowing down by about 2. Now, I'm not going to put all the numbers on here. The most important thing about this, the thing I want everyone to learn at this point, is what the shape is of the graphs. Okay, constant velocity, constant speed, velocity has a direction, right? Constant speed is a diagonal line on a distance time graph. That makes sense because our rise over run, or our speed, isn't changing. Okay, at this point, during that instantaneous time, she decided to run faster. So what does that do? That's a straight line up. She slowly changed speeds. Okay, and it didn't take her any time to do that. Realistically, that's not how reality works. Chances are it did take her like a millisecond to change speed, so it's a little diagonal, but not much. And then we know she started slowing down. This is probably dramatic. The curve probably looks more like a slow, steady curve, right? And she slowed down. But this is basically what we got. By the way, my x-axis is really curvy there. That's better. Anyway, so these are the 3 important points of what happened. Okay, now let's look at our velocity time graph. Okay, velocity over time. Well, what happened here? Well, we had a velocity of 5 kilometers per hour. That lasted for 10 minutes. So we'll go to 10. And look, that's just a straight line. Why is that a straight line? Because it's a constant velocity, and it's a velocity time graph, so it stayed the same the whole time. All right, then suddenly we jumped up speeds to 10. So 10 kilometers per hour. So we jumped up. Same thing, it was semi-instant. So like I said, reality, nothing's instant. So we could do that if we want. Okay, we have a slight slope on that. We have an acceleration, right? even though it doesn't look like an acceleration here. There's some sort of acceleration. Okay, so then what happens? Well, she started to slow down. Did she slow down by a really specific amount, or did she slow down by different amounts? Did she change her acceleration? Well, she had one amount for acceleration. So what we should see is that the slope of this line is in fact at -2, right? Because acceleration, constant acceleration on a velocity time graph will end up being a diagonal line. Just like constant velocity was a diagonal line over here. This may seem a little confusing, but just as long as we have our points, and keep in mind what is forward and what is backwards. We did not have positive acceleration. Positive acceleration would have been this curve kind of going up, right? But we said she slowed down. Sorry, over here would have been a curve going up. Because it's slowing down, it's a curve going down, or velocity time, it's that. Now, they look similar, but you can tell there's difference, especially right here, where she started at 0 time, and kept at that same speed the whole time. So anyway, and really this should have been distance, but that's fine. These are the shapes of the graph. They kind of look like sickles, don't they? Like a little, like, you know, death. Which physics isn't death, even though everything's physics. Anyway, that's physics. That's my pen. Scott's a nerd. And I'll see you guys later.